Okay, hello and welcome to a new week. This week we will talk about counting, which is a fun little topic that you kind of learned a whole lot about already, maybe back in high school. We're just going to solidify those concepts. And then we're also going to bring in set theory because that's what people like to make math out of. Okay, so let us start with some definitions and then we'll get into some examples. Okay, so what I'm about to talk about is called the sum rule and the product rule, and they only work for finite sets right now, okay? Just think about it in terms of finite sets. So you got a cloud and you have points that you can count. It's not like you have a cloud full of all the natural numbers or something, okay? Finite sets only for these rules. Okay, so the first one is the product rule, and it's saying a very natural thing to say. If you have A ways to do one thing and B ways to do some other thing, then that means you have A times B ways of performing both things, both actions. So say you want to choose, I don't know, you want to choose an ice cream. That's like your first set of things that you get to choose from. And then like you can choose if you want sprinkles or something. So these like I for ice cream and S for if you want sprinkles. So the idea is you can separately pick which ice cream you want and if you want sprinkles or no sprinkles. So you have 3 times 2 combinations. I shouldn't say combinations. 3 times 2 ways of picking an ice cream and then picking whether or not you want sprinkles. Okay? And the way that we can formalize this is that we have 2 sets and our options are elements. Each option is an element of I cross S. Okay? Because like I want vanilla with sprinkles. That's just an ordered pair. See that? And you have 6 different ones. Okay? It's just trying to say that, yeah, just trying to make the statement that, okay, if you take the Cartesian product of a bunch of sets, the size of that is the size of each individual set multiplied together. Okay, so that's the product rule. How about the sum rule now? All right, so this is just saying if you have A ways of doing one thing and B ways of doing another thing, so same A and B, and you also can't do both at the same time, okay, that's key, then there are A plus B ways to choose something to do, okay? So I guess you can kind of think of it as like themes. So you have options to do different things. Like here's the set of adventures you could go on. You could go hiking. You could go, I don't know, swimming, etc. You could do all those things. Or maybe you feel like staying in. You could like watch a movie, eat dinner. And so like you want to pick one of these options from either set to do today. And so your total number of options is just going to be 4, right? It's the sum of the sizes of each individual set, okay? And the key thing here is that none of those sets that have ways of doing stuff, A and B, none of those can overlap, okay? Because if A1 had some elements of A2, then this doesn't actually hold, okay? And we'll talk about that later in these slides. So that's the product rule and sum rule. Those are the 2 key ones that I want you to remember. Then the bijection rule is extra. It's still very cool though. So the bijection rule just says if you have a bijection from one set to another, so remember what that looks like. It's like it has to look like this. Doesn't matter how you do it, but you're going to end up having the same number of elements being mapped to the same number of elements, because if there's an inverse, you have to be able to go backwards and remember where you were. Okay? So if you have a bijection, then the 2 sets had to have had the same cardinality. You can't have a bijection from a 3 set to a 2 set, or vice versa. Okay? So yeah, this is just the mathematical way of saying that. If you have a bijection, then the sizes must be the same. And this one actually works for infinite sets, which is fun. Okay, so that's the sum and product rules. These are key terms before we talk about anything else at all. Okay, so keep those in your mind for the rest of these slides. So now let's talk about the generalized product rule, which will lead us to fun things. Okay? So my example here is, it is the cat meme Olympics, and we have 15 contestants on the field today. All right? So we want to figure out, before the game happens, how many different ways could we possibly give out gold, silver, or bronze medals. Okay? That's the example. And so we have to think about this. Okay? And I guess this is the way. This is the way I want to teach you if you haven't learned it yet already. So there are 15 people. Like, first you line them up, and then you say, okay, how many of these people could win gold right now? And the idea is we're counting, so any of them. This person could win gold, this person can win gold. Everybody, all 15, could have won the gold medal. We don't know yet. Okay, so there's 15 people who could win gold, so we can give the gold medal to somebody, and without loss of generality, hey, we can then pick, okay, who would win the silver medal? That means 14 people are left who could possibly win silver. You can't win both gold and silver. That's the idea. So, okay, we only have 14 options now out of the 15 to give the silver medal to. So maybe this person over here gets it. Yeah? That's the key. That's the idea. And then finally, after you've picked gold and silver, it doesn't matter who you gave it to, because you can swap people, it doesn't really matter. Then you have 13 options left for who gets the, sorry, not silver, bronze. Okay? So, the answer is, this is the product rule again, isn't it? You had A ways of giving gold, B ways of giving silver, C ways of giving bronze, 15, 14, and 13. Multiply them together to get all the ways of doing everything together. Yeah? So there's 2,730 ways to give out these medals. Okay, this is 2,730 different ways for the game to be played. Okay, and to end up. All right, so that is this process of okay, 15 people can get the first thing, then there's only 14 left, there's one less. This is called the generalized product rule. Okay, so just keep that in mind, and we're not really going to be using this a whole lot. We're going to be really caring about permutations, which are defined using this rule. Okay, so that's the generalized product rule. So first, before we move on, let's have some examples for you. Okay, so here are a bunch of sets. We've got some sets of digits, lowercase letters, and special characters. So I want you to figure out how many passwords you can make out of these characters that satisfy these constraints. Okay, so they have to be of length. Your password has to be 5, 6, or 7 in length, and then the characters can be any of these, but the first character can't be a letter. Okay, so keep that in mind, and then try and figure out how many passwords would satisfy these constraints. And then we'll do it together. Okay, and this is a game of splitting it up. It's always about that. So our answer is going to be the union of a bunch of little sets that we're going to develop. Okay, it's like we're making little functions to split up the process in math. Okay, so you could have length 5. I have a length 5 set. I'll make a length 6 set and a length 7 set. They're all disjoint. So whatever the answer is, it's the size of all these sets union together. Okay, so it's going to end up being the sum of their cardinalities. And then we have to figure out, okay, what are all the ways we can make a length 5 password, a length 6, and a length 7 password? Okay, so what is the size of all the length 5 passwords? Well, okay, here's what happens. The first character cannot be a letter. So the first character must be a digit or a special character. I'll call this D, L, and S. All right? So the first character must be, okay, how many ways are there of choosing either a digit or a special character? I don't know, let's just add the sets. So D plus S. So that's the first character. And then we have to pick the rest of the characters. How many ways are there of picking the rest of the characters? Well, the characters can be anything after the first, so it's just how many options do we have? D plus L plus S. And how many characters do we have to write now? If this is length 5, we had the first character, and how many characters left? 4. Okay, so you can pick this one for the second character, this one for the third character, and just keep on multiplying. Okay, so this is the size of the set that keeps track of all the length 5 passwords. Okay, this is the rest of the characters. And you'll do the same thing for length 6. Okay, I'll do length 6 maybe quickly, and then I think you can understand what length 7 would be. Size of length 6 is going to be, again, this, because the first character cannot be a letter. It can be either a digit or a special character. And then you have the rest of the characters, and there's 5 left because it's length 6. You already picked the first one. Figure out how to make the other 5 characters. D plus L plus S to the 5. Okay, and I think you can understand what length 7 should be. So whatever this number is, it's probably very large. The answer is the sum of all of these. Okay, so hopefully you're getting that, and that answer is making sense. Okay, let's move on now to a different one for you. This one's more close to home. So we can have license plates in California, at least for now. We're about to run out of space, I think. But we follow digit, letter, 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 digit, 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 right? When you have an uncustomized license plate. So how many license plate numbers are possible if no digit or letter appears more than once? Okay, so this one's interesting. No digit or letter appears more than once. Okay, so keep that in mind because it's different than what you might think. Okay. All right. Hopefully you have a good answer now. Let's try to do it together. So, if no digit or letter can appear more than once, here's what happens. Okay. The first thing we need to pick for this license plate is a digit, and there are 10 of them, 0 through 9, right? So, 0, 1 through 9, and then you have A, B, all the way to Z. So there's 10 of those and 26 of those, right? And we're not repeating things, which is interesting. It's kind of like the metals here. So the first digit can be any of the 10, okay? And then we have a letter. We haven't used any letters yet, so we have 26 options for the first letter. Then for the next letter, because we're not trying to duplicate any letters or numbers, we only have 25 options for that letter, okay? And then for the third letter, we've used 2 letters. We have to pick some of the other ones, okay? So we only have 24 left to choose from. See how it's being whittled down? And then we have 3 digits left, which means we have not 10 options anymore. We have 9 for the second digit that appears, okay? Because we already used 1 digit here. We can't use that one again, so we have 9 left to choose from, okay? And then I think you can understand that it's 987. So whatever this answer is, whatever this big number is the answer, okay? And hopefully you see how we're whittling down these numbers from 10 to 9 to 8 to 7, and from 26 to 25 and 24. That's what happens when you can't repeat things. When you can repeat things, you just start using powers, okay? That's the idea. Okay, so we're counting. Isn't this fun? All right, so on to kind of the main course. We're ready for permutations. Okay, so a permutation, there's 2 different ways of having a permutation, and 2 definitions. So there's just like a regular permutation that we kind of talk about in real life, and then there's also something called an R permutation, which is a bit more mathy, okay? But they're both useful and good to know about. Okay, so if I say permutation without the letter R, I mean this first one, okay? So a permutation just by itself is a sequence that contains each element of a finite set exactly once, okay? So if my set, I don't know, if my set A is like 1, 2, 3, 4, A permutation of this set is a way of arranging these elements in a certain order. So like I can pick the order 2, 1, 3, 4. That's a permutation of the elements of A. Of the elements of A. Okay. And so another permutation would be like 3, 1, 2, 4. Okay, you have all of these different kinds. Okay, and the idea is a permutation. How many do you have? N factorial, or n is the size of the set. Okay. Yeah. Different permutations. Okay. Where n is the size of the set, because here initially, like this set's of size 4, we could potentially put 4 things here. And then the next one, we've already picked one. The next element of the permutation has to be one of 3. Then the third one has to be one of 2. Then you're kind of stuck on the last one because you've picked everybody else. Okay? So the number of permutations of this set A is going to be 4 times 3 times 2 times 1, which equals 4 factorial, which is the size of the set factorial. Okay? That is what it means to be a permutation, and this is how many permutations there are, how many different ones there are. Okay? Not too bad. Now, let's talk about our permutations. So, sometimes we don't want to rearrange every element of the set, we just want to pick a few out and figure out how many different ways we could make a smaller sequence using the elements of a set. Okay, so still with A, here is a 2 permutation. Like 1, 4 is a 2 permutation of A. Like so is 2, 3. So R, I guess. So R, 2, 3, 4, 3, 1, 2, etc. Okay? Those are 2 permutations of the set. They are sequences of length 2 using elements of A. Okay? So now the question is, okay, how many are there of these? And before we get there, we have to do some more notation. So if you're trying to ask how many of these different 2 permutations are there, you say P 4, 2, because this is the style. This is the number of permutations. Number of R permutations from a set with n elements, just like that. You say P n, R. It's like a function call. And it just so happens that the number is going to be n factorial over n minus r factorial. Okay? Why is that? Why are there n factorial over n minus r factorial 2 permutations of the set A? So let's discover why. So for this first element of the permutation, you could pick 4 options, okay? Because there's 4 things to choose from. For the second element, you've already picked 1, you have 3 left, okay? This is the number of our permutations, or sorry, number of 2 permutations. P 4, 2 equals this, and I'm going to show you just hand-wavily why that's also n factorial over n minus r factorial. So here's n factorial, 3 times 2 times 1, and here's n minus r factorial, which is n minus r is 2, right? And then 2 factorial is 2 times 1, and what? Look at that. Hey, so that's why it's like that, right? And using this notation, the number of actual real original permutations is just saying pnn, okay? So you're trying to make length n sequences, okay? That is the idea. And so because permutations have order to them, like there's a first element of the permutation, a second element of the permutation, permutations are tuples, which means you can't rearrange the elements. Order matters. Yeah, that's the idea. Okay, so those are permutations. Isn't that fun? Lots of factorials from now on. So hopefully this is all coming back to us. So yeah, let's have a fun little example of this new notation. So a recent thing was that I think last semester South Africa had a lottery. I think they had plenty of those, but this particular lottery drawing was investigated by the by the police after they drew the numbers 5, 6, 7, 8, 9, and 10 in that order. Isn't that crazy? That is what happened. And the odds, the reason they investigated this is because the odds were very, very slim of that ever really happening. Okay? So the odds of this happening are 1 over P50, 6, because they had 50 balls to choose from. Like, you know, the way that they choose lottery numbers, they have like a little machine with balls that are all moving around. So number of lottery balls, that's a Y. And then number that we're picking. And so how many different ways are there to pick lottery balls numbered 1 through 50? How many ways are there to pick 6 of them out of the 50? Okay. That's what P50 over 6 is. And what are the odds of us picking this particular one? This is the element of the permutation, of the 3, 4, 5, 6 permutation. 5, 6, 7, 8, 9, 10. Okay? Where you could have picked any permutation. That's what the lottery is. It could be any number from 1 to 50. It could be like 50, 42, 187. Okay? And I guess there's one other number, 23. The odds of you getting just this one are 1 over the amount, right? Which is 1 over 50 times 49 times all those things. And it is a 1 in 11.5-ish billion chance. Isn't that crazy? So that is why they thought it was faked or a hoax. And yeah, we had some angry people, I guess, in South Africa. So that happened, and that was something that we can study with our knowledge of permutations. Isn't that fun? Okay, now a question for you. So let's pretend that there is a wedding and everybody is lining up for a photograph, maybe 10 people, like all the people that were in the front or something. Okay, so 10 members of a wedding party, they're lining up in a row for a photograph, and we want to count how many different ways are there to line up these 10 people if you must always make sure that the groom is to the immediate left of the bride in the photo. Okay? So for some reason, they always want to be on this side of each other. But you can put the other people anywhere else. Okay? So give that some thought, and then we'll come back and do it together. Okay. So I guess the key thing here, I'm going to draw a picture, and let's pretend that we're looking at everybody's backs so that I can actually write the bride here and the groom actually on the left. That's just easier for me to think about. So we're looking at their backs right now. And then we can put the rest of the party anywhere else. We can put people on this side, as many as we want. And then we can put other people on this side, as many as we want. They can be anywhere. Okay? As long as the groom is right next to the bride on the left side. So the secret is, if you found it, is to consider the groom and the bride together as a unit, because they must stay in the same order. They can only be moved around in that order, but they could go anywhere. They're just like another person at that point, but they're 2 people together. They can go anywhere you want to put them, but they must be right next to each other. So you just count them as one thing. Okay? So that's the secret. All right? So first, you pick a spot for them. Like, there's going to be 10 members, and you want to figure out, there's going to be 9 options to put people now, okay? Because the bride and the groom count as one person now. That's the secret. So, the idea is, where do you want to put these guys? Think of their place as a number from 1 to 9, right? Because one of these is the bride and the groom, and the rest are the other people, so it adds up to 10 people total. So the first thing you need to do is, out of these, pick which spot you want to put the bride and groom, okay? And there's nine numbers that you could assign to them in the place in this line, yeah? So this is different places that you could put the bride and the groom. together in this particular order that they want to be in, and then you can pick the rest of the people, okay? Times the rest, okay? And then where do you put the next person? Well, you have 8 options. You can pick another number for them, and then 7 options for the next one. Yeah, all the way down to 1. So it's 9 factorial, okay? That is the number of different ways you could line up 10 people if the groom must be right next to the bride on a certain side, okay? The idea is you consider them as just one person now, because they must move together and stay in that order. Okay, so that is, that is the key. That is the idea. So now let's move away from counting permutations to counting subsets. Okay, so let's try and figure out ways of counting different subsets now, not just a set order like permutations are, but where order doesn't really matter, because subsets they don't care about the order. Okay, so the first question, just to jog our memories, is how many subsets of a size 5 set are there? And the answer is, you take the power set. What's the size of any power set? It's 2 to the size of the original set. So that's 32, right? 2, 4, 8, 16, 32. Yes? That's nice. So that's how many subsets there are total. Subsets total. But maybe we want to break this down. Like, how many subsets of size 1 are there? That one's easy. There's going to be 5. You can just put each element in a set by itself. How many subsets of size 5 are there? Well, that's the same size as the original set. There's only the original set. There's just one way to do that. And then we can ask the question, well, okay, how about subsets of size 3? And that is where our intuition doesn't really have anything to say. All right, so let's try and discover how to count how many subsets are there of a certain size. All right, let's try and solve this one. How many size 3 subsets are there of that size 5 set? Like, what does that mean? The trick is to notice that permutations actually help us here. If you ask for P53, that's going to tell you how many permutations of this set there are of length 3. Yeah? So they all look like this. So the issue there, though, is that you end up overcounting things. Okay? You overcount because you see all of these different permutations. There's the permutation 1, 2, 3, 1, 3, 2, 2, 1, 3, all of these. All of these different permutations exist, and they all just contain, they're supposed to represent the subset 1, 2, 3, where the order doesn't matter. So all of these stand for the same subset, unfortunately. So we're overcounting, okay? That is the problem. We are overcounting because of that. But this is mostly there, okay? If we just kind of get rid of this overcounting, we have the answer, right? So let's figure this out. The order of this size 3 subset doesn't matter. So how many times for each possible permutation do we end up counting it? Okay? How many times do we end up overcounting it, or counting it in total? Each time we see a permutation of these 3 elements, how many are there? Okay? How many times do we see them? It's, well, how many ways are there to order 1, 2, and 3? That's what permutations mean. 3 factorial. Okay? So that's 6 times. Every different one. Like, there are 6 ways of arranging the subset 1, 4, 5 as well. Okay? You got 1, 4, 5, 1, 5, 4. There's still 6 ways. Okay? So there's 6 ways for everybody. And let's just divide so we don't have to count everything multiple times. Okay? So what that means is we can take this amount, P53, and if we just divide it by the factorial of this subset size, which in our case is 3, we have the real answer for the number of subsets of size 3. Yeah? Isn't that crazy? So the real answer then is the count equals P53 over 3 factorial. Okay? So that is the idea. And so we can break this down a little bit more, but I won't go to the final answer. 5. How many ways are there out of 5 things to choose 3 of them in any order. 5 times 4 times 3, and then again over 3 factorial, 3 times 2 times 1. So it's apparently 20 over 2, which is 10. Hey, isn't that nice? That is the idea. That is the answer. So, yeah, that's where I want to leave you there. There are 10 different subsets of that size. And there's a name for this process of counting the number of subsets. It's called finding combinations. Okay, so instead of permutations, we have combinations. Okay, so just remember that. And so we have more notation, of course. So we say CNR, or N choose R, and it sometimes looks like this. Okay, that is the idea. So NR, we pronounce this as N choose R. Okay, this is the number of R subsets, so subsets of size R, or also R combinations of size R, in a set with N elements total. Okay, so what we just discovered before was 5 choose 3 equals 10. Okay, and there's a formula for that. We just discovered it, of course, so it's P and R over R factorial, and this simplifies to this. Okay, that's the idea, and the whole point is we're dividing by all these ways we could repeat ourselves, right? And we don't like those because we have sets. Okay, order doesn't matter. That's the point. So yeah, a combination is a set, and this is in contrast to a permutation, which is a tuple. Okay, order doesn't matter. That's the idea. And so I'm pretty sure you're still required to learn about this stuff in high school because I was taught it, right? And so back when your math teachers were telling you, like, okay, we're learning about combinations today, order doesn't matter, and they just moved on, this is what they were saying. They were talking about sets, really. Okay, that is the idea. So we have just discovered combinations, and now I want you to practice it. Okay, so here's a set that's got 6 elements, A, B, C, D, and F. How many subsets of S, so you're going to find some kind of combination, how many subsets of S have either 2 or 3 elements? Okay, so try and give that one a go. And here's the idea. Let's make sure I'm actually recording, yes. So let's find the number of size 2 subsets and the number of size 3 subsets, okay? So that's the goal. So let's do that separately. Find size 2 subsets and size 3 subsets. Okay, and then we can just add those together. Okay, so the number of size 2 subsets is, are you ready? 6 choose 2. How many ways are there to make a size 2 subset out of a set of 6 elements? Plus 6 choose 3. Okay, and if we want to follow these definitions, it's going to be, okay, n factorial over, let's see here, n factorial over r factorial 6 times 5 times 4 times 3 times 2 times 1 over r factorial is 3 times 2 times 1, and then we also have to multiply on top, on the bottom, by n minus r factorial, and that happens to be 3 again. 3 times 2 times 1. Isn't that crazy? For, I guess I was doing 6 choose 3, so maybe I should split this up a little bit. But this is the 6 choose 3 part, and I think you can see that these are going to cancel out, and that's why I just wrote it like this last time. So let me actually do this one first. Sorry. How many ways are there to permute 2 elements out of a size 6 set, 6 times 5, over 2 factorial, which is just 2. 2 times 1. Okay, and then we add 6 choose 3, which is 6 times 5 times 4. You go 3 times over 3 factorial, 3 times 2 times 1. Okay, so that's the answer. I'll let you figure out how big it was, but that is the idea. It's just 6 choose 2 plus 6 choose 3. It's a very easy to write once we know this kind of notation. Okay, so that is combinations. Now let's do something in between, which is fun. Let's do permutations, but this time we get to have repetitions. Oh man. So this is what we have here. When you have a permutation with repetition, it means you're trying to order a set of items, but some of those items are identical to each other. So some orderings would get double counted if we tried to do the combination method, for example. Okay? Or sorry, the permutation method. That is the idea. So how many permutations of the letters are there in LOL? Well, the idea is we need to understand that these L's are the same. Because, look, if these L's weren't the same, like it was L1, like the set was made of L1, O, and then L2, L1, O, L2 is different from L2, O, L1. You see that? And so this is what permutations would give you. They give you both of these. But really, we know that we have the same L. So we end up double counting it because the permutation would use the first L here and the second L here, or in another permutation, it would make the second L go here and the first L go here. And those are really the same L, right? This is the same string. We don't want to double count it. Hopefully that made sense. That was a bit of a rant, sorry. So, yeah, how many real permutations are there of LOL? It's, well, you have LLO, O, L, L, and then O can be in the middle as well. L, O, L, and I think that's it. Once you pick a spot for O, you have just a bunch of L's left, and you got to fill those in. So I think it's just 3. Okay, that is the goal. And yeah, so some permutations are going to be the same as others, and we don't want to double count, even though we would expect permutations to work this time. Okay, so the answer is to use combinations as well. All right, so before we go to Beyonce, the way of doing this is noticing that you have 3 spots to fill for LOL. Okay, we're going to try and permute these letters, and you have 3 spots to fill, 1, 2, and 3. And we can put any letter anywhere. Okay, the idea is we have to choose which places get the L's. Okay, and so we have a size 3 set to choose from. We're trying to assign L to be the L's to go in like 1 and 2, or 2 and 3, or 3 and 1. How many different ways are there to assign an L to these 2 L's to a slot? Well, we have 3 slots and 2 L's, and that just so happens to be 6 over 2, which is 3 ways to do it. Okay? You could have LL, you could have LL, or you could have LL. And that's where the subsets get us the nice fact that these are the same. Okay, so pick the L, pick the spots for the 2 L's, and then pick the spot for the O, and there's only 1 spot left for the O. So spots for L's, and let me explain this slower now, and we'll try and permute all the letters in Beyonce. Okay, so how many different ways are there to do this? Here's the idea. We have 7 letters this time. Okay, 1, 2, 3, 4, 5, 6, 7. We can arrange them however we want, but we don't want to overcount. Okay, we have all these different slots, and we want to say like, okay, the B goes to slot 4 in this particular permutation, the C goes to slot 5, etc. Okay, what we want to do first is pick which of these numbers get the E's, because those are the ones that are doubled. Okay, and so what we do is figure out all the different ways of combining, like all the different combinations of these numbers, 2 of them. Okay, because we've got to pick 2 slots for the E's out of 7 slots total. Okay, That's where 7 choose 2 comes into play. There are 7 locations for those 2 E's. And so maybe like we pick these slots. Okay? The first E is no different than the second E, and this is why we need to use combinations. Okay? And then for everything else, we have to just like, okay, without loss of generality, we have 5 slots left, whatever numbers they were. Just figure out all the different ways to permute the rest of the letters. Okay? And there's 5 factorial ways of those. So the answer is 7 choose 2 ways to permute the E's, and then ways like slots to pick for the E's, and then 5 factorial ways to arrange the rest of the letters in Beyonce. Okay? So hopefully that's making a bit more sense now. You have to use permutation knowledge and combination knowledge to get this, because you don't want to overcount permutations with repetitions. Okay? And so there's actually a formula for this. There's an even fancier formula. So let's try this another time, and then see if we can generalize this idea. So let's do Mississippi. So you got some S's. You got 4 S's that are doubled up. You've got a bunch of I's. 1, 2, 3, 4 I's that are doubled up, and then you have 2 P's that are doubled up. Okay, so we want to scramble all these letters. All right, how many different ways are there to scramble Mississippi? And that is 4, 8, 9, 10, 11 different 11 characters total. Okay, so the idea is, again, we have 11 spots to fill. 1, 2, 3, 4. We need to figure out all the ways that we can fill them. 8, 9, 10, 11. They all get to hold a character. Okay? And now we need to figure out which things to put where. Okay? So we have 4 S's. We have 4 S's. We need to figure out which of these 11 slots will hold the 4 S's. Okay? How many different ways are there to put 4 S's in each of these, in 4 of these slots? Okay? So the idea is we have 11 slots to fill, 4 S's to put somewhere, 4 S's to place. There's 11 choose 4 ways of doing that. Okay? That's the idea. And then let's figure out how to place the I's. We have 4 I's now. Okay? We have 4 I's, and we need to place them in the other slots. So maybe we chose that the S's are going to go here for this particular permutation. We're going to try all of them, of course. Then how many slots are left to fill by the I's? How many places could we choose from for the I's? 7. 11 minus the 4 that we already picked for. Now there's 7 slots left to put an I somewhere. Okay? And there's 4 I's. How many ways are there to do that? 7 choose 4. Yeah? See how this is happening? And then we have 2 P's. Okay? 2 P's to place. So maybe we put the I's like here. Where can we put the 2 P's? Well, we have 3 slots left now. And 2 P's to place. So how many ways are there to do that? Ways of placing 2 things in a size 3 set. 3 choose 2. And then, finally, how many ways are there? I should write this. 4 I's. And then 2 P's. And then after we've placed the P's, there's only 1 slot left for the M. Okay? Times 1. So 1 slot left for the M. And this actually leads to this nice formula, okay? Where, just as usual, we're assigning each character in the string to a number, and that is like where we're eventually going to put it in its permuted form. And so the answer is going to look a bit like this, with a bunch of factorials on the bottom, and let me try and show you that. So all this kind of leads us to it. All right? So what is 11 choose 4? Okay? It's going to be 11 factorial over, and let's do the original definition now, r factorial over n minus r factorial. So 4 factorial over 11 minus 4 factorial. which is 7, right? Times 7 choose 4. 7 factorial over 4 factorial times 7 minus 4 factorial, so that's 3 factorial. Times 3 choose 2, 3 factorial over 2 factorial times 3 minus 2 factorial, which is 1 factorial. And then times, okay, how many different ways are there to permute this? Well, just pretend that's in a set by itself. So you do 1 choose 1, right? 1 factorial over 1 factorial minus, or times 1 minus 1 factorial, which is 0 factorial, which is defined to be 1. Okay, so that's still 1. So this is essentially 1 at the bottom here, but we can keep it like this. 1 factorial times 0 factorial, that's fine. And that goes away to 1. Okay, so here's the pattern. These cancel just like that. And what do we have on the bottom now? It's all the different times that these were repeated. It's the number of S's, it's the number of I's, it's the number of P's, it's the number of M's. Isn't that crazy? And then the only thing left up top was the original number of characters. It's all the permutations. So this is where you get that, okay? This is why this is the answer if you just want to remember a formula. The number of distinct sequences with N1 1s, N2 2s, NKKs, this is how you do it, where you assigned each character in the string to a certain number. That is the idea, okay? And with the repetition, you start dividing by a bunch of factorials. Okay, and they all cancel out beautifully, and that is the formula. Okay, so hopefully that makes a whole lot of sense and you can do it yourself now. Let us confirm that with this example. Okay, so give this a try, and I think this will be the last thing we have for today. We're running out of time, so we'll see. All right, so try permuting the letters in college. And the very first thing you should do is, okay, what is repeated? You got some L's, 2 L's repeated, and then 2 E's repeated, right? So again, we have initially how many slots to fill? 1, 2, 3, 4, 5, 6, 7. So 7 slots, and we got to fill them with all these letters. So I guess we can first pick where to put the L's, all right? 7 slots to fill, 2 L's to put. And then we got 5 slots left to fill. Let's put the E's. 2 E's left. Okay, 5, choose 2. Times, okay, how many different ways are there to put the rest of these? Well, it's going to end up being 3 factorial, right? So C, O, and G are not repeated, so they could be in any order. So how many different ways are there of doing that? It's just going to be 3 factorial. Okay, and this ends up following this formula. If you want to expand it out, it's going to be, let's see here, 7 factorial over, there are 2 repeated L's, 2 repeated E's, so 2 factorial times 2 factorial, and then the rest of these are just a bunch of 1 factorials, because there's 1 C, there's 1 O, there's 1, there's 1 G, yeah. And so this is just times a bunch of 1 factorials. Let's just write them out just for fun. And so that ends up being equal to that, is what I'm trying to say. Okay, so that's how that'll work, and that is the answer. Okay, so you can either use the formula or write it out. At least right now I'd prefer it if you did it in this style, because that shows that you're understanding it. Okay, but obviously on the homework, as long as you get the right answer, I'm happy. Okay, okay, maybe a couple more slides. Okay, just a few more, and that'll leave us in a good spot for next time. So let's talk about counting not sets, not permutations, but this weird thing called a multiset. Okay, it's weird. So a multiset is a odd thing. It makes no sense given what we know so far. So it's a collection. It's just like a set, but it can have multiple things. The order doesn't matter, but it can have multiple things. It's crazy. So that same thing that you can repeat, we say that it's indistinguishable, so the order still doesn't matter, but the count does now. Okay, so this is a multiset. Okay, same notation for sets, which is unfortunate, but you can have multiple elements. It's not actually equal to 1, 2, 7 in this case. Okay, the number of 7s matters. The duplication matters. Okay, but each 7 we consider it to be the same as the other 7. Okay, it's not like 7 sub 1, 7 sub 2. It's the same 7. Okay, it's just duplicated. So this is useful to talk about many things and to prove stuff, because like I'm sure you'd prefer to talk about your wallet having this much money instead of this much money, even though because you have duplicated bills, right? That's the whole point. So that's a good reason to want to use these things called multisets. So our goal for counting multisets, how many different ways are there to arrange a multiset of things? The idea is the questions are going to look like this. So like, given an infinite supply of things, figure out how to fill a basket with n items from m different varieties. And so the duplication means we can choose the same thing a bunch of times, but we only have n items that we can fit in our basket. Okay? So here's my example, and we'll do it on the next slide, and I think that'll be it. So let's pretend that we have our basket, and it can hold 10 dogs, or maybe puppies or something, and we have 4 different breeds to choose from. So here's my basket that will hold our dogs, and you have 4 different breeds to choose from, like, I don't know, Golden Retriever, Labrador Retriever, Corgi, and I don't know, Chihuahua. That's the idea. Okay? So you can put as many of each in this basket, but you can only hold 10 dogs. So the question is, how many different ways could we do this? Okay? We also consider dogs of the same breed to be indistinguishable. So it doesn't matter which 4 golden retrievers you pick and put in your basket, as long as like you just pick 4 of them. The 4 is what matters. Okay, that's the idea. So multisets and counting them, it's a useful thing to want to do. So let's talk about the secret. Okay, let's talk about the formula. So let's do it for the dog example. So the idea is, imagine that each outcome is a binary string, which is going to be odd. It's made up of 1s and 0s, right? That's what a binary string is. And here's the secret. Here's the secret encoding of that string for choosing this. Okay, so we got 10 dogs, 4 breeds. 10 dogs to choose, 4 breeds to choose from. Here's how you can represent a choice for your basket. You can say, okay, for the first breed, for the golden retrievers, I'm going to take 1, 2, 3, 4 of them. Okay? Or not to confuse you with this 4. Let's say I'm going to take 3 golden retrievers. I can mark that. I can represent this as a binary string with 3 1s. And then I'm ready to choose the next one. Let's choose how many labs I want. Let's say that I want 5 labs. How do I represent the fact that I'm changing my choice from golden retrievers to labs? Oh man, I can just put a 0. This separates the breeds. This separates my choices. The 0 is just a separator. I think it's aerator. Sorry if I spelled that wrong. That's the key. That is the key right there, that 0. And then you just, like, you're counting with 1. That's like you're doing it like that. Okay, so now it's saying that I want 5 labs, and then maybe I'll take, what was the next one? 2 corgis, that's 7, 5, 8. 2 corgis, and then no chihuahuas. Okay, so there's 10 1s total. And there's no 1s over there. So 3, 5, and 2. I'm pretty sure, yeah, it's 10. This is how you can encode what you want. And then the problem becomes figuring out how many different kinds of these special strings can we make. And that solves the original problem. You see that? That's fun. So, yeah, the idea is if you want to do this, the number of ways to select n objects from a set of m varieties is this. You just pick where you want these zeros to go, okay? So it's equivalent to picking where you want the zeros to go in the binary string. Because that determines exactly what you want. You always have to have 10 ones. You got to pick 10 things. The zeros to go in the string. You're forced to have 10 ones. You're forced to have n ones. Okay? So, why is it this? It's, okay, we have how many slots to put a 0 in? Well, it's going to be the original n plus m minus 1. Okay? So that's how many spots that we have in our string. That's always going to be the same length. And then how many zeros can we pick? We got to separate them, so we only need one less than the actual number of varieties. Okay, so it's m minus 1. Isn't that crazy? And this means, this is assuming that you can take as much of each as you want. Okay, and you have as many. Okay, so for the dog example, that means that the answer is, we've got 10 dogs to put in our basket, 4 breeds minus 1 over 4 minus 1. That is the answer, okay? Because it's these strings. We got to put a bunch of ones. We got to pick 10 dogs from somewhere. So I got 10 ones. And then our choice in the matter is where we put these zeros to separate, okay, I'm done picking the labs. I'm ready to pick corgis now. Okay? Isn't that fun? So that is how you count multisets. And I think that's a great place to stop. All right? So we'll come back next time and try and remember what we just learned. And I think that all sounds good to me. So I will see you in the next lecture.